A copper pipe shown in figure has an outside diameter DO equal to 90 and the wall thickness T is equal to 8 mm. The pipe is subjected to uniformly distributed torque T of 400 Newton mm per mm along its entire length. Calculate the value of the shear stress at A on the outer surface of the pipe and the shear stress at B on the outer surface of the pipe. So you have to calculate here the value of the tau A. To calculate the value of tau A, we required the total torque at A, that equal to TA, as well as we have to calculate the value of tau B. For that one, we require the value of TB. Value of TA and TB we can calculate by method of integration. This one is a uniformly distributed torque T is equal to 400 Newton mm per mm. Outside diameter is given as DO is equal to 90 mm and the thickness T is given as 8 mm. From this we can calculate the value of DI, which will be equal to DO minus 2 times the thickness, that is we have 90 minus 2 times thickness equal to 8, which one equal to 74 mm. Once we know DI and DO, we can calculate the value of constant K, which is the ratio of internal diameter DI divided by external diameter equal to DO, which is equal to 74 divided by 90. 74 divided by 90, so constant K will be equal to 0.822. To find out the torque at A, we set up our axis at the free end and this distance equal to x. In this case, from the free end, the distance XA will be equal to 1200 plus 2400. So we have 1200 plus 2400, that equal to 3600. This unit is mm. So the distance of point B from free end is equal to 2400 mm. So first of all, we'll calculate here the total torque TA. So total torque TA will be simply the integral of T multiplied by dx, and we have limit is from 0 to XA. That is we have integral from 0 and we have XA equal to 3600. The value of T is known to us is equal to 400. So this value of T is same as 400 Newton mm. So we'll put for T is equal to 400 multiplied by dx. Integral of dx will be same as x, 400 is constant. So we'll get this value equal to 400 multiplied by 3600. This total answer will be Newton mm. Once we know the total torque TA and we have a hollow shaft, so we can calculate here the shear stress at A. So we have TA equal to pi by 16 into DO cube into 1 minus K to the power 4 multiplied by the maximum shear at the outer surface at A. Torque already known to us is 400. So we have 400 into 3600 is equal to pi 16. Outer diameter DO is equal to 90. So we have 90 cube into 1 minus K. K is equal to 0.822. 0.822 power is 4 multiplied by the maximum shear at A. So the maximum shear at A is come out to be 18.5 megapascal. Now the same procedure will repeat for point B also, only that the limit will change from XA to XB. Rest procedure is remains same. So we have total torque at point B is given as integral 0 to XB T dx. This time we have XB is equal to 2400. So we'll get a torque at B. The torque at B will be same as equal to 400 multiplied by 2400. Unit of this one is same as Newton mm. Because of the hollow shaft, we have torque at B will be equal to pi by 16 DO cube into 1 minus K to the power 4, and we can calculate the maximum shear stress at B. Torque at B is same as 400 2400. DO is equal to 90. K is equal to 0.822. So we can calculate the shear stress at B. So just substitute here all value and solve for maximum shear. Same thing that we have done initially also. So the maximum shear at B will be equal to 12.41 megapascal. And the maximum shear at A come out to be 18.5 megapascal. This value will go on increasing and the maximum value will be at fixed end. At free end, the shear stress will be equal to 0. Then will be higher value at B and again higher value at A, and the highest value will be at fixed end. The solid shaft shown in the figure is subjected to uniformly distributed torsional loading T is equal to 7 kilonewton meter and a concentrated external torque of Td equal to 2500 Newton meter. So this value is a counterclockwise, which one is considered at point D. At between B and C we have a clockwise torque of 7 kilonewton meter, and between A and B we have 7 kilonewton meter is again a counterclockwise. Determine the minimum required diameter of the shaft if the allowable shear stress for the metal is 100 megapascal. So this value of 100 megapascal you have to assign the maximum value, and you have to find out whether the torque at A, at B, at C and D, which one is the maximum torque. So our objective here is to find out the maximum torque first. So again we set our axis at D and we can calculate the value of torque by method of integration. At x equal to 0 we have constant torque at point D, that is Td value is equal to 2500. Between C and D no torque is acting, so the torque is remain constant from D to C and is equal to 2500 Newton meter. So no torque is acting from C to D. In that case the torque at D and C is same, that equal to 2500 Newton meter. But between B and C the torque is decreasing, so this value will take as a negative value, this value will take as a positive value, and this value will take as a positive value. So this value will be positive, this is negative, and this one is positive. So between B and C the torque is decreasing uniformly at a rate of 7 kilonewton meter per meter. So the torque is decreasing uniformly from C to B at a rate of minus 7 kilonewton meter. Previously at C we have torque is equal to 2500, so we can calculate the torque in the shaft B as TB. So we have TB is equal to TC minus T, and the length is equal to BC. That length you have to take in meter. So we have TC is equal to 2500 minus T. The torque T has a unit of kilonewton meter per meter, and at D we have 2500. So in Newton meter T is equal to 7000. But length you have to take is meter, and meter equal to 1.2. So 2500 minus 7000 into 1.2, you will get a torque at B is equal to minus 5900. So torque at D is 2500, torque at C is equal to 2500, torque at B is minus 5900 Newton meter. Up till now the absolute value of the torque is maximum at point B, but you have to continue this up to point A also. But between A and B the torque is increasing because it acts in the same direction of 2500. So you have to treat this value positive. Again this value of T is equal to 7000 Newton meter per meter. So you have to take the length equal to 0.5 meter. Previously at point B we know the torque equal to minus 5900. So torque in the shaft at A, that will be equal to TA. Previous value we have TB. This is acting in the same direction, so positive, multiplied by T multiplied by length of AB. TB is same as equal to minus 5900 plus T is equal to 7000 and length AB equal to 0.5 meter. So in this case we'll get the TA, that is the torque at fixed end, is equal to minus 2400 Newton meter. This value is also less magnitude wise as compared to B. It means that our maximum torque will be at B. So the design is based on the maximum torque. So the largest torque magnitude wise is maximum at B, that equal to 5900. So you have to use this torque for designing purpose. So we have TB will be equal to pi by 16 into d cube into tau. Tau is allowed equal to 100. TB is equal to 5900, that is Newton meter. So we'll multiply by 10 to the power 3 is equal to pi divided by 16 into diameter cube. Allowable shear stress equal to 100. Solve this, you will get the diameter D is close to 67 mm. So this is how you can handle the problem when we have given the torque intensity may be uniform, may be varying in given section. So just compute the torque at each section, identify the maximum torque, then use that torque for designing purpose and find the diameter D. Let's consider here we have a torsion member with a non-uniform radius and with a constant load at the free end, and we want to find out here the twist angle equal to theta at the free end by application of the torque T. Since here we have the diameter equal to D1 and this diameter equal to D2, so we'll consider here one section. Before this we'll extend the frustum of a cone into cone. So this one is the frustum of a cone. This diameter is D1, this diameter equal to D2. In this case the torque is remain constant, value of the G is remain constant, but the diameter is changing with respect to x, and therefore we have to take here the variable value of the polar moment of inertia. That is, the polar moment of inertia is the function of x. So let's say here T is the torque, Jx, which one is a function of x, is the polar moment of inertia is a function of x, G is the modulus of rigidity. So we can calculate value of theta by method of integration whenever we have the torque is a function or J is a function or G is a function. So we have theta equal to integral 0 to L. Torque is remain constant here, G is remain constant. Polar moment of inertia is a function of x multiplied by dx. We solve this integral and we'll find out here the value of theta, that is the angle of twist. For this one you have to do the construction here and you have to develop the relation for radius or diameter at any distance x. We'll assume here the diameter at the free end is equal to D, diameter at the fixed end equal to 2D. So for this special case we'll find out here the angle of twist. L is the length of the shaft and T is the torque applied at the free end. So if you extend the frustum of cone, they will meet at a point O. So from O you have to measure the length. Now since here we have a reduction is from 2D to D over a length L, so remaining length will be also equal to L, that is from D to 0. So in the first segment, that is the length L, diameter has been changed from 2D to D, that is 2D minus D equal to D. So in the next segment, that is length equal to L, diameter will be D minus 0. So we'll set our axis system at point O. If I take the half section, then this radius will be equal to D by 2 is equal to R. So this radius will be equal to 2R. So at this point here, we'll set our axis and we'll consider one element which has a valid range from L to 2L. So let's consider here that we have one element whose radius equal to R and this element at distance equal to x from the reference point. And let's say we have the length of this element equal to dx. So we want to develop here the relation between R, the distance x, and the radius R. For this one we'll consider the symmetrical triangle. One symmetrical triangle is this largest triangle, which one is the right angle triangle whose height equal to 2R and the base is equal to L plus L is equal to 2L. Then we'll consider this triangle, which one is again a right angle triangle whose apex is at point O. Then this height will be equal to R and the base will be equal to X. So we can apply here the symmetric triangle, that is the triangle ACO is similar to triangle BDO. So these two are the similar triangles. If you consider these two triangles, then R divided by X, that is the height divided by base, is same as equal to 2R divided by base equal to 2L. So we have this height is equal to R and the base is equal to X. This height is equal to 2R and the total base is equal to 2L. 2 and 2 will cancel out. And at any distance x from point O, we are able to calculate the radius R. So we have radius R is equal to x multiplied by R divided by L. Once we know the radius at any distance x, we can calculate diameter D. Diameter D is simply 2 times of radius, that is 2 times of x multiplied by r divided by length L. Now diameter is a function of x, therefore the polar moment of inertia is also a function of x. So we can find out here the twist in the length dx. So twist in this length dx is given as d theta is equal to t multiplied by dx divided by j, that is the polar moment of inertia, multiplied by the modulus of rigidity g. This value of j you have to write down as pi by 32 into d to the power 4, 2x into r divided by L power is 4. So let's substitute it and we'll develop the equation for d theta first. So d theta term as it is, value of t will be as it is, dx will be as it is, j term you have to replace as pi by 32, d to the power 4 multiplied by the value of g, and this value of d we can replace as 2 times of x multiplied by r divided by L. We'll substitute here and then we'll try to solve this equation. So this 32 will come in numerator. In numerator we have 32 times t multiplied by dx, pi will be as it is, and the value of d will be replaced as 2 times of x into r by L, and the whole power is 4 multiplied by the modulus of dt equal to g. Now you have to solve this equation. So denominator of L will shift in numerator, will become L to the power 4. So we have 32 times t L to the power 4 into dx divided by pi into 2 to the power 4. 2 to the power 4 is 16. So we have 16 pi x to the power 4 r to the power 4 multiplied by g. So the constant term here is 32 divided by 6, that equal to 2 into t L to the power 4 divided by pi. Capital R is the radius, that will be constant value, power is 4 multiplied by g, into dx divided by x to the power 4. So we are ready for this integration and we'll integrate it from, since our shaft is between from origin at a length equal to L to 2L, our limit will be also x equal to L to x equal to 2L, not from 0 to 2L, because shaft is only defined from point O at a distance x equal to L to x equal to 2L. X is measured from O. So just integrate this term, only thing that we have limit is from L to 2L. So we have 2 times t L to the power 4 divided by pi r to the power 4 g, and we have dx x to the power 4. So this constant we can take it outside. Dx x to the power 4 is x to the power minus 4 into dx. That can be solved and can be substituted for L and 2L. So we'll continue this last equation, that is theta is equal to L to 2L, 2 into t into L to the power 4 divided by pi r to the power 4 into g dx divided by x to the power 4. So we can take out here 2 times t L to the power 4 by pi r to the power 4 g constant. So in this case we have theta is equal to 2 times of t multiplied by L to the power 4 divided by pi into r to the power 4 multiplied by g, and we have integral of x to the power minus 4 is x to the power minus 4 plus 1, that equal to minus 3 divided by minus 3, and we have limit is from L to 2L. So this minus 3 we can shift outside the bracket. In that case we will get minus 2 times t L to the power 4 divided by 3 times of pi into r to the power 4 multiplied by g, and here we have x to the power minus 3. X to the power minus 3 is same as 1 by x cube. 1 by x cube is upper limit is 2L. So we have 1 upon 2L cube is same as equal to 8L cube minus 1 upon L cube, that will be lower limit. Now L cube can be taken common here. So we have minus 2 times t L to the power 4 divided by 3 pi into r to the power 4 into g, and L cube we can take it common. What is left is 1 by 8. So we'll take out here 8 common. So we have 1 minus this one is 1, so it will be 8. That is we have minus 7 by 8. So this 2 and 8 will become 4 here. So this 2 will cancel out, and here we have 4. 4 into 3 is 12, and in numerator we have minus 7. So in numerator you will get 7, and denominator we have 3 into 4 is 12. So we have 7 by 12 into t into L to the power 4 divided by pi into R to the power 4, and then we have g. L cube is left in denominator, so 1 L will left in numerator. So finally we have theta is equal to 7 divided by 12 multiplied by t multiplied by L divided by pi into R to the power 4 divided by g. So this one is the expression for the given angle of twist when the diameter is reduces from 2d to d over the length equal to L. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.